I'm going to talk about communication network reliability. So I'm going to present a method that was developed in our group that is called Recursive variance reduction technique. And I'm going to show that this method actually doesn't verify bounded relative error, as the reliability of individual links goes to 1. For this reason, we are going to combine it with importance sampling. And in two ways. First one is what we call balanced importance sampling, where we balance all the probabilities. And the other one is zero variance approximation. Again, the same thing than Daniel presented in a different context. And the same thing than I had also presented yesterday, and Jose and so on. So, okay. So the outline of the talk is first a general introduction and a description of crude Monte Carlo technique, and then the description of the RESIM algorithm, which is a recursive variance reduction, and which works quite well, but is not very efficient when the individual links have a strong reliability, a high reliability. So that's why we run those two algorithms, balance RVR and the zero variance approximation, in order to get the good efficiency properties. I will end by a numerical result showing how it works. So a short introduction to reliability analysis. So most of you know about that. So the goal here is to compute the probability that a given set of nodes in a network stay connected when the links can fail, and here we assume that nodes are perfect and they do not fail. So this has a lot of applications, especially in telecommunication networks and in a military context and electricity management and so on. So the basic model, we consider an undirected graph that we call G, which is made of a set of nodes and a set of M links that are connecting different nodes, and a subset of the set of nodes that we call the terminal set, that is K here, and that is typically the set of nodes that have to remain connected in the graph. So we assume again that nodes do not fail, and each link can fail with a given probability QE for link E, and our goal is to compute the probability that a given set of nodes, here those three nodes in gray, stay connected given that the links can fail. So if you have this kind of topology, you generate randomly the fact that links work or do not work, and you end up with a given random partial graphs. So in this case, the nodes are not connected. In this case, they are connected, not connected, and so on. So you generate independent graph like this, and you want to compute the expectation of which is the probability that the nodes are connected. So overall, you have a set of 2 to the m configurations, given that you have m links. So computing this is a NPR problem in general, so that's why we are using Monte Carlo simulation. So now we go to the crude Monte Carlo estimator. So how does it work? So we just generate a random state vector x, for which the coordinate E is a Bernoulli random variable, giving 1 if link E is working and 0 otherwise. So from this random state vector, we can use also the structure function phi, which associates to a state vector a value in 0 and 1, such that phi of x is 1 if all the nodes in the subset K are connected when the state vector is x, and 0 otherwise. So the reliability of the network is the expectation of phi of x, and the unreliability, which is 1 minus the reliability, is the expectation of 1 minus phi of x. So how does it work, crude Monte Carlo in this case? So we just generate n independent copies of the state vectors and compute the random variable yi, which is 1 minus phi of xi, for xi the ice copy. And the crude Monte Carlo estimator just computes the average value. And we can easily get a confidence interval thanks to this. But we are mainly interested in the case where the unreliability of the system Q is very small. And there are many contexts for that. This can be due to the fact that there is a large number of paths that may connect the nodes in K, or the context that we are interested in is the case where the individual unreliabilities of individual links goes to 0 in terms of a given parameter epsilon. When epsilon goes to 0, then unreliabilities also of all individual links goes to 0 in different ways. And in that situation, the global unreliability also goes to 0. And in full generality, a property that is interesting to look at is the bounded relative error property. So what we investigate in this case is the relative error, which is a ratio of the standard deviation divided by the expectation of the value, which is basically the half-width, relative half-width of the confidence interval that can be obtained. And for crude Monte Carlo simulation, it is well known that this relative error tends to infinity when the global unreliability goes to 0, which basically means when epsilon tends to 0 in our context. So what we want to find is a new estimator such that this relative error is bounded as the unreliability goes to 0. In that way, to get a specified relative error will become independent on the independent of the number of random variables that are necessary to get that relative error. Okay, so now the recursive variance reduction method. So just consider this small example as an illustration. So the basic idea is just from this from a topology, a graph that we have, we select a K cut set, which is a set of links such that if no link in this cut set works, then the network is not connected anymore. Here you have those 3 links. If those 3 links do not work, then this node is not connected to the others. So computing such a cut set can be done in a polynomial time, in m log m actually. And as soon as we have such a cut set, it is easy to compute the probability of given events such that bj, which means here that the j minus 1 first links of the cut set, if we order them, are down, but the j is up. And computing this probability is immediate from this relation, given that we have independence of failures, of course. And we define pj as the probability that the j minus 1 are down and the j works, given that at least one link is working. So this can be computed very easily too. And how the recursive variance reduction method works, so we just select a cut set, as I said, and compute QC and the PJs, and we choose randomly the first link that is working on the cut set C, and we do this according to the probability distribution Pj. And as a consequence, we know that the j minus 1 first links are failed, so we can remove them from the graph. And for the jth one, we just contract it. And the value y of the estimator from using recursive variance reduction, y RVR of the graph is the probability of the cut set QC plus 1 minus QC times the estimator obtained for the new graph where we have contracted the jth link, and where we have removed the j-1 first link on the cut set. And we can apply it recursively by also working now on this reduced graph. So formally, the estimator that we get is given by this formula. So here we have the probability of the cut set and the conditional probabilities for the different subgraphs that we have. And it is easy to show that the resulting estimator is unbiased, and the second moment can be computed also quite easily. So with this formula, with again those recursive values. And one problem with the method is that it doesn't verify bounded relative error. So here is an illustration, and it also helps to understand how it works. So we just consider this small graph with 3 links, and we want to compute the probability that S and T are connected. So we use this cut set. We order the links, this one first, second, and the third. And so it is easy to see that the probability of the cut set is epsilon to the square, and we can compute the second moment from this formula. And how does it work? So G1 is a subgraph where this link is working, and G2 is a subgraph for which this link is not working, but this one is working. Okay. So if we just contract the graph for G1, so this one is working, so we just contract S and T. So in this case, S and T are in the same node, so they are always connected. So the unreliability is 0, and the second moment is also 0. On the other hand, if this one is not working and this one is working, so we just contract S and U, so we just have now a graph made of one link, and we end up with this situation. And here too we have just a Bernoulli random variable, and we can easily compute the second moment and the first moment. And finally we end up with a second moment in epsilon to the 3, and if we relate it to the square of the first moment, it will be epsilon to the 4. So we don't have bounded relative error. But just as a remark, we may have bounded relative error depending on the ordering of the links. If we reorder in another way, then we can have this property that is verified. So for this reason, we have designed a method called recursive variance reduction technique. And the idea is comes from the fact that the lack of bounded relative error property comes from the crude distribution of the sampling of the first working link on the cut that we have. So using importance sampling, we just want to replace the given values of pj's by new probabilities, pj that we call pj tilde. And the way it works is, just as a reminder, pj is a probability that of the event bj given that at least one link is working on the cut C. And we then have this formula that I record here, where b prime j represents the conditional event bj under the probability pj. So the idea now is just to replace pj by new probabilities pj tilde, and the general formulation by introducing the likelihood ratio here would be this one. And for balance RVR, what we do is that we use a uniform distribution for the first link that is failed on the cut, 1 over the number of links on the cut, and we then end up with this kind of expression for the estimator. And what we can prove in this case is again, of course, that our estimator is unbiased, but also that the estimator verifies the bounded relative error property. So And this can be done quite easily by induction, working on the second moment, and from the second moment and first moment of the subgraph that we have. So another estimator that we have implemented is a so-called zero variance approximation, RVR. So the idea now is not to use a uniform distribution for the PJ tilde, but to choose the first link that is failed on the cut according to this probability, where we use it where we take it proportional to the initial probability, multiplied by the unreliability of the subgraph Gj, and we normalize it to have probability 1 over all the choices. So this gives us this general estimator just by replacing the different values of Pj and Pj tilde. And doing this, it can be proved that this estimator has exactly variance 0. So this is also quite easy to prove just by proving by induction, or by proving that the estimator always gives the good and reliability. But again, here there is a problem. Is the fact that in order to implement it, we need to know those values of Q of the different subgraphs, which is the unreliability of all the graphs. And if we knew it, then we would not need to simulate. So that's why we have to implement something else. And the idea is to replace the given value of Q by a heuristic or a simple approximation of those unreliabilities, and that we will call hat Q. So we just have exactly the same estimator, but Q of the different graphs is replaced by an approximation. And what we can prove is that if we have a sufficiently good approximation of the different unreliabilities of the graph, let's say here that they are of the same order of magnitude as epsilon tends to 0, then our estimator will have the bounded relative error property. So our choice as an approximation is to try to find the a mean cut of the graph, and to use as an approximation the probability of the mean cut that has the maximum probability. So this can be computed anyway. For applying RVR, we had to compute mean cuts. So now we just use the same method, and we use the probability of the mean cut with the maximal probabilities. And if we do that, then we verify this property, this assumption. The probability of the mean cut max prob approximation is of the same order of magnitude than the real unreliability of the subgraph. And in this case, we have bounded relative error. And we can even prove that if we have an asymptotically perfect approximation, then we have a better property, which is vanishing relative error, which means that the relative error tends to 0, which is stronger than just being bounded, as epsilon tends to 0. So this is something that can be proved. So to illustrate how it works, we have used 3 different topologies, which are benchmark topologies. The first one is the ARPANET topology here. The second one is a complete graph with 6 nodes, and third one, the dodecahedron topology. So here we have a lot of different numbers. So the basic idea, you have the 3 different graphs here, dodecahedron, ARPANET, and complete graph with 6 nodes, and different unreliabilities of individual links. We just consider the homogeneous case here, and the different unreliabilities that can be computed, and the different variance of a single random variable for the standard Monte Carlo, RVR, balance method, and approximate zero variance. And the next table will be maybe more maybe clearer than that. But here we have some numerical problems, but because the values are very small and we are close to the double precision, so that's why is difficult to analyze here. But if we just to have a better view of how it works, we can just compute the relative error for the three methods. Here you have for the RVR, here for the balance method and the approximate zero variance. And you can see that for RVR, for the ARPANET topology, then relative error is increasing as the unreliability goes to 0. And actually, for the complete graph, we have the vanishing relative error property even for RVR. And we have a bounded relative error for the Dodecagon topology. For the balanced method, bounded relative error is always verified, so it works fine. But what is interesting to see is that even if it's always verified, there are some cases for the complete graph here where RVR has better properties anyway. And for the approximate zero variance of RVR, then here also we always have bounded relative error and even vanishing relative error, which is kind of what I call perfect estimator as opposed to perfect simulation, because we are getting closer to the real to the zero variance approximator. So this works better than the others, and but I find it interesting to see that even RVR, even if it doesn't verify in general all the good properties, may be better than the others, because in this case it's even it gives exactly the same values and approximate zero variance. So as conclusion, what we have described is asymptotic analysis of RVR algorithm as a links reliability of link goes to 0, and describe two new combination with important sampling. One is balanced RVR, where you use a uniform distribution, and the other one is zero variance approximation that is quite implemented now, as we can see during this workshop. And we have illustrated the gain that can be obtained. And as a remark, also a multinomial version of the algorithm can be performed to get a faster generation of all the different cases and gain in terms of computational time. So I'm done.
So are there any questions? Okay, so I guess I have a question. Did you say that this approach works for when the link probabilities are not uniform? It also holds?
Yeah.
Okay.
It's a bit more complicated to find the mean cut, max probe mean cut approximation, but yeah, it works also.
Okay. And then did you also look at the case of if nodes are unreliable as well?
If no, what do you mean?
So nodes can fail as well as links?
No, but I guess it doesn't change much. It would be about the same kind of analysis. I think so. Yeah, I think, well, you just, your state vector, you just add the number of nodes, the nodes in the state vector, you just increase the dimension of the problem, but that's it.
The computation of cuts will be more complicated, because now you must extend it, but it will work. And it can be done. Other people can work with cuts composed of links and nodes.
So, any other questions? Okay, so let's thank the speaker once again.